Let's take a look at this other example of a block diagram. This is an example from Ogata's book. We're simply going to reduce the entire block diagram to a single block by applying block algebra reduction method. Remember that the reduction table is available for download on the website, and the link is in the description of this video. We'll be using all the operations covered in the first video of this series. So to start, let's look at where we should begin tackling this problem so we can start simplifying it. If we look at the innermost part here, where we have a branch point next to a summing point, let's remember again that this is an operation that either can't be done or is very complicated, so we should avoid it at all times. The same applies if we look at this other point here. We have a summing point next to a branch point. There's not much we can do there for now either in that spot, because a sum next to a branch is something we should avoid. So what we can do initially is take two summing points these we can work with, and as we've already seen, we can swap these two summing points. So that's exactly what we did. I moved this summing point to the left and this one here to the right. As you can see here, even after moving those two summing points, you can see the result. Here we go back, and after moving them, you can see that the diagram is now a bit more organized. The next step we're going to take is here, at the innermost point. We know that since the summing point can't be modified with this branch point, we won't touch that. But the branch point can be moved to the other side of this G2 block. If I do that, moving this point to the left side of G2, I can apply equation number 8 from our table, which tells us that when we move this branch point to the left, this is what we get. So it simply tells us that we need to replicate the same block along the feedback path. In other words, this G2 has to go along the feedback path, meaning it should go down here and connect with H2. So we do this. We move this branch point. Thank you. And we place G2 in the feedback path. In this case, it ends up here, right next to H2. Once again, applying equation number 8 from the table. Now then, here we have two branch points. We know that all of this here, all this line that goes up and down, it's all exactly the same point. And since these are 2 points that are exactly the same, I can swap them without any issue, placing this branch point on the left and the other one on the right. Let's do that. And additionally, since we have two blocks in series, we know that we can combine them into a single block, as we see here, which in this case represents a multiplication of H2 by G2. If we do that, we end up with our block of H2 times G2. And here we can see that I swapped the two branch points, and we can even appreciate it more clearly as this block diagram is becoming more organized here. Starting from the innermost part, you can see that this is the typical representation of a closed loop, which is equation number 13, one of the ones we've used the most in these videos. The only difference here is that in the direct path, for example, as we have it in the equation, we usually have a block. But in this case, there isn't a block if there's no block. It's simply a 1. And here we have the feedback loop. So we apply this equation, and now we would have it in the direct path. In this case, since G1 didn't exist, we put a 1. So here it's 1 divided by 1 plus H2 times G2. And we can see it here. It's 1 divided by 1 plus H2 times G2, which is exactly what's shown here. A feedback block using this equation. The comment section of this channel is always open for the control community, both men and women who actively follow the channel. I would like to know, what is the biggest challenge you face? For example, with these block diagram topics, what is it that still isn't clear to you? Or what is the greatest difficulty you encounter in control system? Well, that's one of the main themes of this channel, and the idea is to create videos to keep helping you. So I'll see you all in the comment section. Here we also have another structure that we see here, which is also very familiar. These are two blocks in parallel. We simply have H1 in parallel with G2. Both are being added together. We've already seen that we can apply equation number 5 for two blocks in parallel. In this case, with the formula G1 in parallel with G2, we simply reduce it to a single block, which is G1 plus G2. Let's do that here. A single block, that would be H1 plus G2. Very good, perfect. This block diagram is becoming clearer and clearer. So let's move on to these three blocks that are in series. Once again, we can apply concept number 4, which is that all blocks in series, I can simply combine them into a single block by multiplying them together. So let's multiply these three blocks. When we multiply them, we see that there is a 1 on top. Here we have G2 times H1, which would be this 2, which becomes 2 times H1 times G3. And in the denominator, we simply have the feedback, which would be 1 plus H2 times G2. And so we have the reduction here. This block, then would be R. Once again, we have it here so you don't get lost, which was simply applying equation number 4 here. So now we can see that we have another feedback loop here, which means we can once again apply equation number 13 from our table. That's the feedback equation. We're really becoming experts at this feedback process. In this case, once again, it's negative feedback. That's why here, in the denominator, it will be positive. Before we continue solving this problem, I invite you to click on this card if you want to become completely an expert in control systems. So let's do the feedback calculation, which would be the forward block. In this case, which one is the forward block? R divided by 1 plus the forward block times the feedback block. In other words, 1 plus R times H3. If we do that, the forward block is R divided by 1 plus R times H3. Let's substitute the value of R. This is the value for all of this. If we proceed and apply algebra here, we simply keep reducing the denominator, cancel these two denominators, and we'll arrive at this expression. So, the entire reduction of this green box would be simplified to a single block, which would be this operation, mathematically. So here we have the reduction of that block, which we'll call V again. So now I have V here, and I can once again use equation number 13, which would be the direct loop. In this case, it's K1 times V, as we have here, with feedback here, since we have negative feedback. So, plus 1 plus the direct loop, which in this case is K1 times V again, K1 times V times the feedback. But for the feedback, I don't have anything. So it's a unity feedback, which means we just multiply by 1, and the 1 is simply omitted. If we substitute the value of V, it equals all of this. Here, we can proceed mathematically, starting with the denominator, and we'll cancel out the denominators here. We'll arrive at this final expression, where we've managed to reduce the entire block diagram to this mathematical expression. In this way, we started with an initial example, which was this one here, and we managed to reduce it to a single block using block algebra. To reach this representation of my block diagram, we successfully reduced our block system to a single block. Now it's time to check if this reduction is correct. For that, we'll use Simulink software and compare the two responses. I want to let you know that the solutions to all these exercises are available for download on the website, and the link is in the description of this video. Additionally, the Simulink simulation files are also available, so you can have them on hand. Here we are in MATLAB. First, we need to open the file here, example 1M. In this file, all the default blocks will be loaded. So, we first need to run and click R so that each of the blocks G1, G2, G3, and G4 are loaded. We need to do this before proceeding to open the Simulink model. Once we've done that, in this case, it's called example 1, which is this one right here. I'm going to double click it to open it up right here. So we have our original diagram, and down here we have the reduced version we've obtained. Let's see if they're equivalent. To do that, we're going to run a simulation. Once the simulation is finished, we'll observe the response of this block diagram to a step input. We simply click here on the scope, and we can see that it has an oscillatory response, and it more or less stabilizes at about 0.32, more or less perfect. So did the reduction of our block reach the same result? Let's take a look here, then at the output of our reduced block to see what it's giving us. Let's double click it again. It shows an oscillatory response and stabilizes at 1.32. It's exactly the same response. But just to be sure, here is another. Scope, which is the comparison. It's taking the signal from the complete block, and on the other side, the signal from our reduced block. Let's double click it, and we can see that both are identical. Here, it should display a yellow line and a blue line. The yellow line corresponds to the complete block diagram, and the blue line corresponds to the reduced one. In this case, since they are identical, the blue line is overlapping the yellow line. That's why we don't see the yellow line, which tells us that both systems are equivalent, and that we have properly reduced our block diagram system. If you keep practicing with exercises, you'll develop tremendous skill in this area of block diagram. So to get started, subscribe to this channel by clicking on my photo and check out the Control Systems playlist. I invite you to watch our 4th example on block algebra and leave me a comment. What did you think of this example? And are you really learning how to solve these problems?